Hey guys, today we're going to look at how to graph polynomial functions. Now the whole point of this lesson is that we're going to look at a polynomial equation and gather as much information that we can from that equation so that we can eventually put it on a graph. Now in order to understand polynomial functions, let's look at the difference between a monomial and a polynomial. A monomial, as mono suggests, is where you have one term. So some number a, which would be the coefficient, x raised to the n. Now n is the exponent, obviously, but it's also called the degree of the function. In terms of a polynomial is when you add or subtract multiple terms, as poly suggests, poly meaning many. So basically, the degree of a polynomial function would be the highest exponent of all of the terms. Keep in mind that, just so that you understand my vocabulary, a term are all of those parts that are being added or subtracted. So for example, in this particular polynomial function, we have 1, 2, 3, 4 terms. Now the degree here, what you would do is scan your polynomial and look for the highest exponent. So the degree would be 5. Now the leading coefficient is the number that is attached to the variable with that highest exponent, which in this case is 8. This term right here, that first one, which in a polynomial function, it should be written in standard form, meaning from highest exponent to the lowest exponent. That first term with the term with the highest exponent, that is called the leading term. So in the case of this particular polynomial, the leading term is 8x to the 5th. Now let's look at some examples of polynomial graphs. So a polynomial graph is defined to be continuous and have smooth, rounded terms. Continuous basically means, in a really simple definition, is that you can trace the graph without lifting your finger from left to right. So for example, if we look at this one here, I could trace it and I didn't have to lift my pen one time, and I was able to trace the entire graph. Additionally, these are all smooth curves. There are no sharp points. So this would be considered a polynomial function. This second one here, yes, it is continuous. I can trace the entire thing without lifting my pen. However, we have here a sharp point. And in order for this to be considered a polynomial function, it would have to be smooth curves. So this is not a polynomial function. In fact, if you recall when we were doing transformations, this is the absolute value graph. Remember that absolute value always looks like a V on a graph. When we look at this one down here, again, I could trace this without lifting my pen. It's smooth, rounded curves. So this would be considered a polynomial function. This last one here, if I were to try tracing it, I would have to lift my pen in order to continue. So this would not be considered a polynomial function because it is not continuous. So now let's start looking at all of the qualities that we can find based on the polynomial equation. The first thing we're going to look at is the leading term test. Now the leading term test tells us the end behavior of a graph. Now what is end behavior? End behavior basically tells us what the function is doing at the ends, right? So how the graph is behaving at the end, hence end behavior. So what we would do is we're looking for, let's say, on the right side of the graph, if it's going up or down, or the left side of the graph, if it's going up or down. So all polynomial functions will have two end behavior statements, one for the left side and one for the right side. In Algebra 2, we wrote end behavior like this, as x is approaching, that's what the arrow means, approaching, negative infinity. This indicates the left side of the graph because as you go to the left, the x values become more negative towards negative infinity. F of x is approaching. So at this point, what we would do is look at what the y values, since f of x represents the y's, and we would look at what the y values are doing on the left side of the graph. Let's say, for example, my graph looked like this. On the left side of the graph, we see that it's going down. So f of x would also go towards negative infinity. Now, without a graph, if we have the equation, the leading term tells us the end behavior of the graph. And what we do is we have to take note of two things, the degree and the leading coefficient. So the degree, we would look at whether that is an odd or an even number. And the leading coefficient, we don't care about the actual number, we're just checking the sign. As a rule, the sign of the leading coefficient tells us the right side of the graph. So I'm just going to write this down. So if the leading coefficient is positive, that means that the right side of the graph will go up. If the leading coefficient is negative, then that means that the right side will go down. Regardless, the leading coefficient will always tell you the right side. Now, whether the degree is odd or even will tell us the left side. If the degree is odd, then that means that the ends will go in opposite directions. So think O for opposite. Then if the degree is even, that means that the ends will go in the same direction. So if the right side is going up, then that means that the left side would also go up. So let's actually put this into practice. Here we have all the possible scenarios for our end behavior. If n is odd, meaning if you have an odd degree, so let's just say x to the third, the degree is odd. And the leading coefficient is positive, which here it's a positive 1. So because the coefficient is positive, that means that the right side is going to go up. And since the degree is odd, that means that the left side has to go in the opposite direction, meaning it's going down. And you can see that on the graph here. Now, like I said, we wrote in Algebra 2 our end behavior statements like this. But in pre-calculus, the whole point of this course is to prepare you for calculus. So we are going to use calculus notation, which are limits. That's what the LIM stands for. That means the limit. And a limit is defined as the intended y value of the graph. I say intended because, for example, if we're looking for the end behavior, if the end behavior is as f of x is approaching infinity, the y values are intending to go towards infinity. It will never actually reach infinity because infinity is not a real number. So let's look at this notation and so we can understand it. So we're looking for the limit as x is approaching, because remember that's what the arrow represents, approaching negative infinity. So this is the left side of the graph. So I would look at my left side and I see that my f of x, my y values, are going down. So this means that the limit as x is approaching negative infinity of f of x is equal to negative infinity. Now for this statement, the limit as x is approaching positive infinity, that means we're looking at the right side of the graph because my x's will go towards positive infinity on the right. My f of x, my y values, as we can see here, are also going up. So that's how you would fill out these limit statements. And again, I call this a statement because when you read it in your head, even though this is mathematical notation, it's basically like a sentence. The limit as x is approaching negative infinity of f of x is negative infinity. Now let's look at when the degree is odd, but the leading coefficient is negative. So I'm just going to use the example of negative 2x to the 7th. First, I notice my coefficient here is negative. So again, remember the coefficient tells you the right side. Since it's negative, my right side of the graph is going down. And because my degree is odd, that means that the other side of the graph has to go in the opposite direction, which is why here it is going up. So now to fill out these limit statements, the limit as x is approaching negative infinity, so the left, of f of x, since it's going up, we would say positive infinity. The limit as x is approaching positive infinity, so now the right side of my graph, we see it's going down, so f of x is negative infinity. Now here we're going to look in these two examples when the exponent is even. So if the degree of your polynomial is even and your coefficient is positive, so let's use the example of 3x to the fourth. First, I notice here it's positive, so that means the right side is going to go up. And since my exponent here is an even number, that means that the left side will also go up. Now to fill out these limit statements, the limit as x is approaching negative infinity, so the left side, f of x is approaching positive infinity because it is going up. And the limit as x is approaching positive infinity, so the right side of my graph here, that means f of x is also approaching positive infinity. And this last example here, this is for when the degree is even and your leading coefficient is negative. So let's say negative 5x to the 6. Again, the negative tells us that the right side is going down, and the even exponent tells us that the left side is going in the same direction. So the answer to both of these limit statements, since both of these ends are going down, would be negative infinity as well as negative infinity. So that's our end behavior. So now let's practice that. Here we have h of x is equal to x to the third minus 2x squared. First, I would determine my leading term, which I'm just going to use LT to represent leading term, which we see here is the one with the highest exponent, so x to the third. This has a positive coefficient, meaning the right side is going to go up. And because the exponent is odd, that means the left side is going to go in the opposite direction, so down. So what I do is that I kind of draw arrows, one for the left and one for the right, so that way it helps me to write out those limit statements. So here we go. Let's write the limit as x is approaching negative infinity of f of x, this is the left side of the graph, is going to equal to, and I look at the left arrow, which is going down, so we would say negative infinity. Now keep in mind that your limit statements for end behavior always start the same. The only thing that changes is the actual answer. And remember, you'll always have two limit statements, one for the left side, which we just wrote, and now one for the right side. The limit as x is approaching positive infinity of f of x is equal to, and because the right arrow is going up, we would say positive infinity. In this next example, I look for my highest exponent, which is 3x to the fourth. So that's my leading term. Now, since the coefficient is positive, that means the right side will go up. And since my exponent is an even number, that means the left side goes in the same direction, so also up. So that means that the answer to both of my limit statements would be positive infinity, since both of these arrows are going up. So the limit as x is approaching negative infinity is positive infinity, and the limit as x is approaching positive infinity of f of x is also equal to infinity. In this example here, now this is not written in standard form because as you can see, the exponents are not in decreasing order. So we have to make sure that we always scan, okay, and you're always going to look for that largest exponent, which is this term right here. So my leading term is negative 2x to the 7th. Now because my leading coefficient is negative, that means that the right side is going to go down. Oops, and I put up. Just kidding. Let's try that again. So the right side is going to go down. And since my exponent here is odd, that means that the left side goes in the opposite direction, so up. So now to write our limit statements. The limit as x is approaching negative infinity of f of x, so this is the left side, so I'm going to look at my left arrow here. It's going up, so we write positive infinity. And the limit as x is approaching positive infinity of f of x, Now we look at the right side, which is going down. So we would say negative infinity. Now, if you look at these two examples here, these are written in factored form because you can see that we have all of those individual factors that we would need to multiply to then write the equation in polynomial standard form. In order to determine the leading term, we need this in standard form. However, notice that in all of these examples, we didn't use any of those other terms. We just used the leading term. So instead of having to multiply everything out, because that would be very time consuming, A, and B, there's a lot of room for error if you were to try to multiply everything out. So instead, what we do is we take the leading term of each individual factor along with any exponents and multiply them together. Because if we were to multiply the entire polynomial out, that's exactly what we would get for the leading term. So this is one factor, which is a monomial, and so therefore that's my leading term. In the x minus 1 squared, my leading term is x, but it will eventually get squared. And then for the x plus 5, my leading term is x. So I would multiply negative 4x to the third with x, and then it's being squared, so squared, and then times that third x, which gives us a leading term of negative 4x to the 6. Remembering that when you're multiplying variables, you add the exponents. 3 plus 2 plus 1 is 6. So now let's draw our arrows. Because the leading coefficient is negative, that means that the right side is going to go down. And since the exponent is even, that means that the left side will go in the same direction, so also down. So that means that both of my limit statements would be equal to negative infinity. So the limit as x is approaching negative infinity of f of x, so the left side, is equal to negative infinity because it's going down. And the limit as x is approaching positive infinity of f of x, so my right arrow, is also equal to negative infinity. Last example here, we have 2x to the third times x minus 1 times x plus 5. So I'm going to multiply the leading term from each individual factor. That means that my leading term is going to be 2x to the third times x, which is equal to 2x to the fifth. So now, because my leading coefficient is positive, that means that the right side will go up. And because my exponent is odd, that means the left side goes in the opposite direction. So now let's write our limit statements since I have my arrows ready to go. The limit as x is approaching negative infinity of f of x, so my left arrow, we see it's going down, is equal to negative infinity. And the limit as x is approaching positive infinity of f of x, since my right side is going up, we would say it is approaching positive infinity. Now that we've gone through the leading term test, we're going to get some more additional information about our polynomial equations. So what we've done so far is we figured out what the ends of a polynomial are doing. But now we need to figure out what the middle section of the polynomial is doing so that we can accurately graph. So in order to do that, one of the most important things to find would be those x-intercepts, which remember is also called the zeros of the function. So a polynomial function of degree n, whatever the degree is, has at most n distinct real zeros. So if your polynomial function has a degree of 5, that means that it'll have 5 zeros, or 5 x-intercepts. And at most n minus 1 turning points, meaning one less turning points. And a turning point is this. If I had a polynomial function that looks like that, then my turning point is when it changes from increasing to decreasing or decreasing to increasing. So for example, which by the way occurs at your extrema, so the maximums and minimums. So this would be a turning point, this would be a turning point, this one here, and here as well. So this particular graph, makeshift graph, has 4 turning points. So that means that this is probably a fifth degree polynomial. So here we have this equation, x to the third plus 3x squared minus x minus 3. So remember, by definition, the zeros, the x-intercepts, are the values of x for which f of x is equal to 0, meaning that we would have to set this equation equal to 0 in order to find those x-intercepts. So just by looking at the equation, I can tell that we're going to have 3 x-intercepts. And turning points, it would have at most 2. So notice that these here, it says at most and at most. So this fundamental theorem of algebra, because that's what that's called, if you have the degree is 3, it will have at most 3 x-intercepts, meaning that it could have less, but it won't have more. And same thing for the turning points. It will have at most 2 turning points. Again, not more, but it could have less. Okay, so in order to find these x-intercepts, what we're going to have to do is not only set the equation equal to 0. Again, that's why it's called a 0, is because it equals to 0. But we're going to have to factor. And factoring is a big concept or topic that we have to cover when we're finding these x-intercepts. When you have 4 terms, the best way to factor is to factor by grouping. Because you have 4, that means I can group the first 2 together and the second 2 together. So that's a clue. 4 terms, factor by grouping. So what we do here when we're factoring by grouping is we take the first 2 and we look at what these 2 terms here have in common. What can I factor out? So meaning the greatest common factor. And we can see that in terms of the numbers, I can't factor out any numbers, but they both have at least an x squared, because this means that there's 3 x's and this means that there's 2. So I'm going to factor out an x squared, meaning that when I factor it out, I would have x plus 3 left. Remember that when you're factoring, this is like undistributing. So if you're ever unsure if you did this correctly, you can kind of think of what it would look like if you were to distribute and make sure that it equals to what you originally had. So like if I were to distribute this x squared times x is x to the third, and x squared times 3 is 3x squared. So this is factored correctly. Now negative x minus 3. They both have a negative in common. So I'm going to factor out a negative 1. And when I factor out a negative 1, all that does is it changes the signs. So that would give me x plus 3, which equals to 0. At this point, you'll be able to tell if you're factoring correctly, because what is in the parentheses should look exactly the same, which it does. And the factors that look exactly the same, that is one of my factors. Essentially what we're doing is we're factoring out an x plus 3 from each term. And then what's left over, that is your other factor. So x squared minus 1, which equals to 0. Now I hate to break it to you, but we can continue factoring from here. And that's because of this, the x squared minus 1. So this is called a difference of squares. A difference of squares is when you have a difference, meaning that it is subtraction. It's only 2 terms. So that's another clue. 2 terms, a difference. And then we're checking to see if the first term and the second term are squares or perfect squares. A perfect square is something that can be easily square rooted, and it will give you an answer. So for example, the square root of 25, that's a perfect square because the square root of 25 is 5. 16 is a perfect square because the square root of 16 is 4. If you look at these 2 terms, the square root of x squared is x, because the square root and the exponent would cancel. And the square root of 1 is 1, because 1 times 1 is 1. So this is a difference of squares. Now how do we factor a difference of squares? First of all, we have this x plus 3. When you're factoring this, we would open our 2 parentheses. We square root the first term. The square root of x squared is x. We square root the second term. The square root of 1 is 1. Now remember, when you square root a number, the answer is always plus or minus. So that means that these factors would be plus and minus. So x squared minus 1 is x plus 1, x minus 1. And remember, we take this and we make it equal to 0. And now we're going to set each individual factor equal to 0. Because remember, if one factor is equal to 0, 0 times anything would equal to 0. If this factor is equal to 0, doesn't matter what the other two factors are, the whole thing would equal to 0. So that's the principle that we're applying here. So x plus 3 is equal to 0, x plus 1 is equal to 0, and x minus 1 is equal to 0. To get those zeros, or your x-intercepts, x here would equal to negative 3, because we would have to subtract the 3. Here we would have to subtract the 1, so x would equal to negative 1. And here we'd have to add the 1, so x would equal to positive 1. So these are my 3 x-intercepts. Now, just so you can see how all of this comes into play, I'm going to show you the graph of this function. I mean, that's the whole point of getting all this information, is to eventually graph it. So I want you to see exactly how this comes into play. So here's the graph of the polynomial function we were just working with. We can see that we have those x-intercepts at negative 3, negative 1, and 1. We said that there would be at most 2 turning points, which we have one here and one here. And then additionally, if you look at the leading term, the coefficient is positive, so you see that the right side is going up. And since the exponent is odd, that means that the left side will go in the opposite direction, so down. So far what we've gotten is the end behavior, and now these x-intercepts here. And eventually we're going to also figure out how we know what the curves are going to be doing. So let's continue with our lesson. First, let's continue practicing on how to find those zeros. So here we have f of x is equal to negative x to the 4th plus 4x to the 3rd minus 4x squared. Based on the exponent, or the degree of this polynomial, we would say that there would be at most 4 zeros, meaning that we would have at most 3 turning points. Now, to find the zeros, we're going to have to factor. If you look at every single term, we have an x squared for all of them, so we can factor out an x squared. And additionally, when we factor, if there's ever a negative in front of your leading term, we want to factor that out as well, because in case we need to keep factoring, that negative could become problematic. So we're going to factor out a negative x squared. And when I do that, this becomes a positive x squared minus 4x plus 4. So this is how we would factor that negative x squared. And notice that all of the signs changed because I factored out that negative. And now what's inside of the parentheses is a quadratic, which we can factor that by thinking of what two numbers multiply to give you a positive 4 and add to give you a negative 4. The two numbers that multiply to give you a positive 4 would be negative 2 and 2, and negative 2. Negative 2 and negative 2 multiply to give you positive 4, but add to give you negative 4. So this would be x minus 2 and x minus 2. Which, to write this in a more concise way, we would say negative x squared times x minus 2 squared, since there's 2 of them. Now to figure out those zeros, we would have to set each individual factor equal to 0. So negative x squared is equal to 0, and x minus 2 is equal to 0. I didn't have to put the exponent, I didn't have to do like the x minus 2 squared, because if I square root it to cancel out that exponent, the square root of 0 would just be 0. So I can just set what is inside of the actual parentheses equal to 0. And over here for this negative x squared, I would have to divide by a negative. 0 divided by a negative is 0. I'd have to square root. The square root of 0 is 0. So that means that one of my solutions here is just 0. If you ever have a term where it's just x or x squared or negative x squared or negative x to the fifth or x to the seventh, whatever, there is nothing added or subtracted to it, that means that x is just going to equal to 0. In this case here, we would have to add the 2, so x would equal to 2. So we have two x-intercepts at 0 and 2. Now technically, we said that there would be 4 zeros. And like I said, technically, we do have 4. Because this is squared, this is like we have x is equal to 0 2 times. And because this is also squared, that means we have 2x is equal to 2's. So we actually do have 4 zeros. It's just that x is equal to 0 repeats twice, and so does x is equal to 2. Now let's look at b. We have x to the third minus 5x squared plus 6x. Here we can factor out an x, which would give us x squared minus 5x plus 6. What is inside here is a quadratic, so we can open our two parentheses, and the two numbers that multiply to give you a positive 6, but add to give you negative 5 are negative 3 and negative 2. We make this equal to 0. And so we set each individual factor here equal to 0. So here we have 3 zeros. X is equal to 0 is 1. Here I'd have to add the 3, so x is equal to 3. And here I'd have to add the 2, so x is equal to 2. So based on the equation here, since my degree is 3, that means I'm going to have 3 zeros. Meaning that for the number of turning points, it's always 1 less, so we would have at most 2 turning points. And my actual zeros are the 3 that I just solved for, which are 0, 3, and 2. Now let's look at this next one here. Notice that in this one we have 4 terms. And remember that I told you that that would be a clue. If you have 4 terms, you're going to factor by grouping. In this first group, I can factor out an x squared, giving me x plus 2. And here, negative 4x minus 8, they both have a negative 4 in common. So when I factor out a negative 4, that would give me x, right, because I already took out the negative 4, and then negative 8 divided by negative 4 is a positive 2. And remember, as long as what's inside of your parentheses is the same, you factored correctly. So this is equal to x plus 2, and then we have what's left over, which is x squared minus 4. Now look at this term. We have 2 terms. It's a difference. X squared is a perfect square, and 4 is a perfect square. So we can keep factoring this. So you'll need to be able to recognize when you have a difference of squares. If you were to factor x squared minus 4, we have this x plus 2 first. We're going to open our two parentheses to keep factoring that x squared minus 4. The square root of the first term is x. The square root of 4 is 2. And we make 1 plus and 1 minus. So to write this in a more concise way, because I have x plus 2 here twice, we can write x plus 2 squared and then x minus 2. And we make this equal to 0 so we can solve for our zeros. So we have x plus 2 is equal to 0 and x minus 2 is equal to 0. For this one, I would have to subtract the 2, so x is equal to negative 2. And here I'd have to add the 2, so x is equal to 2. So based on my equation here, the number of zeros that I should have is 3, meaning that the number of turning points would be 2. And my actual zeros are negative 2 and 2, which still gives me 3 because at x is equal to negative 2, which is this factor here, x plus 2, since it's squared, that means that x is equal to negative 2 repeats twice, giving me a total of 3 zeros. For this last one here, we have x to the 6th minus 3x to the 5th. They both have an x to the 5th in common, so we're going to factor that out, leaving me with x minus 3. I can't keep factoring here, so that's it. So you set each individual factor equal to 0. Because there's nothing added or subtracted to it, this just means that x is equal to 0. And here I'd have to add the 3, so x is equal to 3. So those are my two zeros, 0 and 3. But based on the equation, we should have 6. That means that we would have 5 turning points. And technically, we do have 6 zeros, because at x is equal to 0, it's going to repeat 5 times. So we have 0 5 times, and then the 3 giving me a total of 6 zeros. Now I'm going to show you another factoring technique. This is called quadratic form. Now quadratic form is only used if you notice that you have a polynomial function that follows this pattern, where the exponent starts with 4, and then it goes to 2, and then there's none. So what we do here is that this actually is very similar to a quadratic equation, and you're going to see that now. What we're going to do is we're going to assign u equal to x squared. That means that if you were to square u, it would equal to x to the 4th. So I would replace x to the 4th with u squared, and I would replace x squared with u. So that would give me u squared minus 5u minus 14. Once I write it like this, you can see that this is a quadratic equation. And we can factor this by doing what we always do. What two numbers multiply to give you negative 14 and add to give you negative 5, which would be negative 7 and positive 2. Now the whole point of this is that we're going to find the real zeros. So you're going to see now what that means. So we make this equal to 0. Now remember that this equation is x, so once you have it factored, we're going to replace u back with the x's. U represents x squared, so I would rewrite this back as x squared minus 7 and x squared plus 2. This is a difference, but 7 is not a perfect square, so I cannot keep factoring this. And this is positive, or rather we're adding, not subtracting, so I can't keep factoring this either. So this is completely factored. So now we're going to take each individual factor and solve for x. Make it equal to 0 and solve for x. For this one, I'd have to add the 7. So x squared is equal to 7. And then I would have to square root. So x would equal to plus or minus the square root of 7. In this one, I'd have to subtract the 2. And I get x squared is equal to negative 2. And then I would have to square root. But when I square root that side, you notice that we have a square root of a negative number, meaning that I have an imaginary solution. So this is still plus or minus, but because of that negative, we're going to take out the I, and it's square root of 2. So technically, this function should have 4 zeros, and we do. We have 2 real zeros and 2 imaginary zeros. So the ones that we are concerned with it from a graphing perspective would be our real zeros. So this would be our solution. Let's practice this a little bit more. This is another example of where we have a polynomial that is in quadratic form. Notice the exponents go from 4 to 2 to none. So I'm going to make u equal to x squared and u squared equal to x to the 4th. And I'm going to substitute it where I see it here. So u squared is minus 9u plus 18. So now we have to open our two parentheses to factor. The two numbers that multiply to give us a positive 18, but add to give you negative 9 are negative 6 and negative 3. And we're going to make this equal to 0. Once it's done factoring, we replace u back with x squared. So this is x squared minus 6 and x squared minus 3. And now we make each individual factor here equal to 0. And now we solve. So here I'd have to add the 6. So x squared is equal to 6. And then we square root. So x would equal to plus or minus the square root of 6. Over here, I'm going to add the 3. So x squared is equal to 3. And then I would square root. So x would equal to plus or minus the square root of 3. So based on the equation, we would have 4 zeros with at most 3 turning points. And those zeros, these are both real numbers, so plus or minus the square root of 6, as well as plus or minus the square root of 3, which gives me those 4 zeros, the positive and the negative square root of 6, and the positive and negative square root of 3. For b here, we have h of x is equal to x to the 5th minus 6x to the 3rd minus 16x. First, I notice that every single term has an x in common, so I would first factor out that x. And that would give me x to the 4th minus 6x squared minus 16. What we have inside here, the parentheses, is written in quadratic form. So for this section, we are going to use u is equal to x squared, and u squared is equal to x to the 4th. So now I'm going to rewrite this. And just so that I don't forget that I still have this x here, I'm going to keep writing it as I continue factoring. So we have that x on the outside, and then we have, this would be u squared minus 6u minus 16. And now we continue factoring. The two numbers that multiply to give us negative 16 and add to give you negative 6 would be negative 8 and positive 2. Now that it's factored, I can replace u back with x squared. So we have the x, we have x squared minus 8, and x squared plus 2. We solve for each individual factor from when it equals to 0. So x is equal to 0, x squared minus 8 is equal to 0, and x squared plus 2 is equal to 0. This, there's nothing to solve for, so this is already one of my solutions. Here I'd have to first add the 8, so x is equal to 8. Then we would square root. So x would equal to plus or minus the square root of 8. Over here, I would have to subtract the 2. So x squared is equal to negative 2. And then we would square root. So x would equal to plus or minus I, since we have the negative inside the square root of 2. So based on my equation, I should have 5 zeros and 4 turning points. And then here, remember, we're only determining the real zeros. So x was equal to 0, as well as plus or minus the square root of 8. Which, keep in mind, the square root of 8 can be simplified. 8 is 4 and 2, and then 4 is 2 and 2. So we can rewrite this also as plus or minus 2 square root of 2. Now, the last piece of information that we need in order to graph our polynomial functions is we're still continuing with these zeros, but we're going to notice what's called the multiplicity of the zero, meaning how many times does that x-intercept repeat. And to kind of demonstrate that, I have here these two basic examples. We have x squared and x to the third. If you were to solve for the zeros, here x squared is equal to 0, so x is equal to 0. And you can see that we have that x-intercept there at 0. Now you'll notice that the graph here only touches the x-axis at that x-intercept, and then it goes back in the same direction. It does not go through the x-axis. This is because there is an even exponent. So if the x-intercept, or your 0, repeats an even number of times, then it will touch the x-axis at that particular point. For x to the third, we still have that x-intercept at x is equal to 0, but because it repeats 3 times, because that's the exponent, that means that it's going to cross the x-axis. And you'll notice that it touches the x-axis and it keeps going. So it goes through it. So if your x-intercept has an odd multiplicity, so repeats an odd number of times, then it will cross the x-axis at that particular point. So let's put this all together because we've already pretty much determined multiplicity of zeros without really calling it that. Like, I'm just going to go back a second so you can see what I mean. For example, here, we had here that x is equal to 0 repeated twice, and then that x is equal to 2 also repeats twice because of that exponent. So the exponent basically tells you the multiplicity of the 0. So let's, like I said, put this all together, okay? So we're going to do the following. We're going to determine the end behavior, which is using the leading term test. Then we're going to state the number of zeros and turning points, because again, that's going to give me more information about our graph. And finally, we're going to find the real zeros by factoring and stating their multiplicity along with its effect on the graph. So here we have my leading term, which is 3x to the fifth. Because my leading coefficient is positive, that means that the right side is going to go up. And because it's an odd exponent, that means that the left side is going to go down because it's got to go in the opposite direction. So to write the end behavior, we would say the limit as x is approaching negative infinity of f of x is equal, so this, remember, represents the left side. It's going down, so negative infinity. Then the limit as x is approaching positive infinity of f of x, so that's the right side, so my right arrow, since it's going up, we would say positive infinity. Now, based on the equation, we should have 5 zeros and at most 4 turning points. Now, let's determine those zeros. So when I scan this equation here, I notice that every single number can be divided by 3, and I can factor out an x to the third as well. So if you're having trouble trying to figure out what your greatest common factor, look at the numbers and see what they're all divisible by, which we've discussed. But in terms of the x's, you can only factor out the least amount. So look for the least amount of x's, which is, in this case, to the third. So we would say that we can factor a 3x to the third. And if I do that, I would get x squared minus 6x plus 9. And I can keep factoring this as well. So I have 3x to the third, the two numbers that would multiply to give me 9 and add to give me negative 6 are negative 3 and negative 3. And a more concise way of writing this would be 3x to the third, x minus 3 squared. And this is going to equal to 0. Now I solve for each individual factor, make it equal to 0. Here, if I divide the 3, it's still 0, and if I cube root it, it's still 0. So x is equal to 0. And here I'd have to add the 3, so x is equal to 3. So let's figure out about the multiplicity and whether it's going to cross the x-axis or touch the x-axis. So at x is equal to 0, when I look here at my factored form, I see that it repeats 3 times. And because 3 is an odd number, that means it will cross the x-axis. For x minus 3, I see that it repeats 2 times, meaning that it will only touch the x-axis. So let's look at that graph. This is the graph of that particular equation. We had gotten that the end behavior for the left side means that it would go down, and for the right side, it would go up. We have our two x-intercepts. At x is equal to 0, since it repeated 3 times, it would cross the x-axis, so you can see how it goes through it. And at x is equal to 3, it only touched the x-axis and went back in the direction that it came from. So all of this matches up with all the information that we got. So that's everything that we need to know in order to graph. So now let's practice graphing a couple of polynomial functions. Now it's important to note that when you're graphing a polynomial, it does not need to be exact. Like for example, with our graph here that I just demonstrated to you, if we don't actually have the graph, we don't know how high or how low it's going to go for those points in between. So you can just estimate. We're basically, for our graphs, we're just trying to get a general idea of what the graph is doing. So let's go ahead and get all the information that we can about this polynomial and see if we can put it on the graph. So first, we're going to apply the leading term test. My leading term here is x to the 4th. So that means since my coefficient is positive, my right side is going to go up. And since it is to the 4th, so an even number, that means that the left side goes in the same direction, so also up. So whenever you're writing end behavior, always write it using limits. So we're going to write the limit as x is approaching negative infinity of f of x is going to equal to positive infinity since the left side goes up. And the limit as x is approaching positive infinity of f of x is equal to positive infinity as well, since it's also going up. Now in the case of this one, in terms of factoring, because we do need to determine the zeros, if you notice, the exponents here go from 4 to 2 to none. So this is where we're going to have to use that quadratic form. So we assign u to equal x squared, and u squared equal to x to the 4th. When I replace everything, I get u squared minus 2 times u plus 1. In terms of factoring, this is u and u, and the two numbers that multiply to give you positive 1, but add to give you negative 2, are negative 1 and negative 1. Or rather, if you prefer, well, let's leave it like this for now. So now we're going to replace u back with x squared. So x squared minus 1 and x squared minus 1. Now notice that this is a difference of squares, right? Because x squared is a perfect square and 1 is a perfect square. So we can factor each one of these to be x plus 1 and x minus 1. So we have 2 of each, since both of which are the same and both are the difference of squares. So to write this in a more precise way, we would say x plus 1 squared and x minus 1 squared. And now we're going to make this equal to 0. If I solve for each one, I get that x is equal to negative 1, because I'd have to subtract the 1, and x is equal to 1, because I'd have to add the 1, both of which have a multiplicity of 2, since the exponents here are 2. So I'm going to write this here as a note. At x is equal to 1 and negative 1, the multiplicity is 2, meaning that it will only touch the x-axis. So the first thing that we're going to do when we're graphing this here is we're going to plot these x-intercepts. So we have at 1 and negative 1. Once you have your x-intercepts, you're going to now attach the end behavior to the outermost x-intercepts. Both ends go up, so I am going to go up here as well as up here. Now the multiplicity is 2 for x is equal to -1, so it's only going to touch the x-axis and then it'll come back up. And now we're going to connect it with the other x-intercept. And notice that when I do that, it touches the x-axis, and then because of my end behavior, it goes back up. So that matches up. So this is my graph. Now I'm going to go ahead and show you the actual graph so you can see how we got this. So this is the graph. And notice how it matches with what we got. Again, we didn't really know how high it would go, but that's okay. Like I said, we just want more or less a general look of what the polynomial would look like. And it looks like we got this right. Let's try another one. Here we have f of x is equal to x to the third minus 3x squared. So first we're going to apply the leading term test. Here my leading coefficient is a positive number, so the right side will go up. And then my exponent is odd, so that means that the left side has to go in the opposite direction. So let's write our limit statements. The limit as x is approaching -infinity of f of x, that's the left side, it's going down. And the limit as x is approaching positive infinity, which is the right side, is positive infinity. So we have our end behavior done. Now let's determine those zeros. X to the third minus 3x squared, they both have an x squared in common. So we're going to factor that out. And that would give me x squared times x minus 3. We make it equal to 0 to solve for our x-intercepts, or our zeros. So here, because this is x squared, that means that x is equal to 0 since nothing was added or subtracted, so that's just 0. And x minus 3 is equal to 0. I'd have to add the 3, so x is equal to 3. Now at x is equal to 0, the multiplicity is 2, meaning that it will only touch the x-axis. For x is equal to 3, the multiplicity is 1, which 1 is an odd number, so that means that it will cross the x-axis. So let's go ahead and put these points on our graph. We have 0 and 3. Now we attach our end behavior. The right side is going up, the left side is going down. At x is equal to 0, the multiplicity is 2, so that means it only touches here at the x-axis, meaning that it'll come back down, but then I have to connect back to my next x-intercept. So when you're looking for the middle section of your graph, once you determine if you're crossing or touching at one x-intercept, then you just go ahead and connect to the next x-intercept. And if we had multiple x-intercepts instead of just 2, like if we had more than 2, you would just continue doing that using the multiplicity to let you know whether you're going to go back in the same direction or go through the x-axis. So now let's look at the graph to make sure that we got this right. Here's the graph of that function. We have the end behavior, the left side was going down, the right side is going up. We had the x-intercept at 0 that only touched the x-axis. And then we had x is equal to 3 where it crossed the x-axis. And again, we didn't know how low it was going to go in between, so we just kind of, it's a guesstimate. But it looks like the actual behavior looks the same as ours, so we're good to go. And that's how you graph polynomial functions.